Chapter 11, Section 3, Automated Process Discovery. In this section, we look into more details of how automated process discovery works. We have already discussed that the input for this automated process discovery is an event log, as the one that you see here. You see that there is a case ID as a column on the left-hand side. We record the name of the task in the next column, and there is also a timestamp. The objective of automated process discovery is to find a process model that best describes this event log in a diagrammatic way. Let's first highlight that process mining is not only a theoretical exercise. There are various commercial process mining tools on the market. They can be roughly distinguished in terms of these four groups that you see here. There are open source process mining tools, such as Apromore and Prom. There are lightweight tools like Disco that support process analysis projects. There are mid-range tools that provide more sophisticated functionality, including Minute, MineVenue, QPR Process Analyzer, Signavio Process Intelligence, Stereologic Discovery Analyst, Lana Labs, and several more. And there are heavyweight tools that integrate with the overall information infrastructure of companies. For example, by integrating with ERP systems. These tools include the RS Process Performance Manager, Celonis Process Mining, Perceptive Process Mining, or Interstage Process Discovery. One of the tools that actually came out of our research efforts is Apromore. It is a tool that was largely developed at QUT Brisbane and later further developed by the University of Tartu and the University of Melbourne. In Apromore, you can store various models and also various event logs. Apromore then provides you a visual representation of these event logs in terms of BPMN process models. Apromore also supports various techniques for identifying subprocesses in our event logs. And it supports conformance checking and identifies parts of the process where the event log differs from the actually predefined process model. Another very popular tool is Fluxicon Disco. In Disco, you load an event log and you get an overview of it by means of different statistics, as you can see here. What is plotted is the case duration and the number of cases that fall into a certain range. For each of the cases, we can inspect when they started and finished and how long they took. With this data, Fluxicon generates a directly follows graph, as you see it here. It gives a visual overview of the process, not only in terms of what are the activities in their sequences, but also in terms of what are the frequencies of these activities and the paths between them. This is very helpful for process analysts to get an overview of the process. These directly follows graphs are very intensively used for process mining. The process map or directly follows graph of an event log is a graph where each activity is represented by one node. And arcs are drawn from activity A to activity B if we have observed in the event log that B was directly following A in at least one of the traces. The arcs in the directly follows graph can be annotated with different pieces of information. We can show how often we have passed from A to B, either absolutely or relatively. And we can also show how much time has elapsed on average. How can we construct such directly follows graphs? Here is a simple example. We have an event log as input, and in this event log we have 3 times the sequence A, B, C, D. Twice we have the event sequence A, C, B, and D, and once we have the event sequence A, E, and D. We can now step by step construct the directly follows graph by progressing through the event log and observing pairs of events that happened one after another. We start with the first sequence ABCD. The first consecutive pair of events that we observe is A followed by B. This translates into the following part of the directly follows graph. We add A, we add B, and a connection between the two of them. We also record that this was observed 3 times. We continue progressing through our event sequences. The next pair we observe is B followed by C. Now we also add C to our directly follows graph, and we annotate 3 to this arc as well. For the first sequence, we finally observe that C is followed by D, and that adds another node to the directly follows graph and a connection from C to D with the number 3 annotated to it. If we continue with that procedure, stepping through each of the sequences that we have observed in the event log, we finally arrive at the following graph. You see that each arc connecting two events is associated with a pair of subsequent events that we observed in at least one of the event log sequences. This is the procedure that is also taken by many process mining tools to construct their visual representations of the event log. Instead of annotating how often we have observed a certain sequence, we can also easily imagine that the average duration is annotated to these arcs here. In practice, the number of events of a particular event log can be very large, and even larger can be the pairs of consecutive activities that we observe. In order to cope with the complexity of these real-world event logs, we have 2 options available. The first option is to abstract. That means we show only the most frequent activities or the most frequent arcs. Or we filter the traces of the event log For example, removing traces that fulfill a certain condition or that violate a certain condition. The need for such filtering and abstraction is highlighted by this example. What we see here is a process map of an event log from a real business process. We see that this model is very complex. This is not a problem of the tool that is showing this process, but it is a problem of the underlying complexity that is in this event log. In this case, the tool that is used here is Celonis. Celonis provides various filtering and abstraction options. In this way, we want to arrive at a model that is more readily understandable. Complex process models, as we see it here, are also sometimes called spaghetti model for the many crossing lines. If we now apply some meaningful abstractions and filterings to this process, you might be surprised how well the process can be understood. Here we have reduced the number of nodes from 100% to 90%. And we are now using 98% of the arcs and not 100% of them. Now we get a much better understanding of this process. The process starts with create application and this application being submitted. Then we observe the event handle leads until we arrive at a point that is called complete application. The status complete application is associated with 3 different loops. The first loop is from complete application to complete application again. That means certain revisions have been done to the application. Or there's also a loop along concept. It is revising the concept. And there is a loop upwards towards accept, create offer, created, and send mail and online. From the complete application status, we can progress towards the right-hand side bottom of this diagram via call after others and validate application. For the validate application status, we observe that there are many ways of continuing, either towards acceptance or via validating to returning, or having incomplete files, or cancellation. Thanks to these filterings and abstractions, we now have a model that a process analyst and a domain expert can understand. Different criteria can be applied for filtering. Filtering rules can be related to events, for example, if they fulfill a certain condition, or if the trace fulfills a certain condition. They can also be related to performance ranges, or to observing a certain sequence by a pair of events, or according to certain endpoints in the process. There are various process mining approaches that create more sophisticated models than the directly follows models that we have just seen. We will look at 4 different process mining techniques that can be used to create BPMN process models. There's the alpha miner. It is simple, but it is not robust. There's the heuristic miner. It transitions from the directly follows graphs that we have seen towards a BPMN model. Then there's the inductive miner that tries to create block structures. and the structured miner that tries to maximize these block structures. Let's start with the alpha miner. The basic idea is that we identify ordering relations in our event log. The first step is to identify the directly follows relationships that we have already seen. The goal is to identify all these directly follows relations in our event log. If A is followed by B, we use the greater as sign from mathematics to represent it. That means it reads A is followed by B. This list of directly follows relations is then used as a basis for determining more complex relationships. A pair of activities like A and B is called causally related if we have observed that A is followed by B, but never B is followed by A. We call two activities as being parallel if we have observed that here in this case B was followed by C and also C was followed by B. Any pair of activities that we never see in any successor relation with one another are in the category of unrelated or exclusive. With the help of these more complex relations, we build a so-called footprint matrix. Let's look again at the log file that we have used in the previous example. Here it is written with mathematical notation. There is the sequence A, B, C, D observed 3 times. The sequence A, C, B, D observed twice. And once we have observed A, E, and D in a sequence. We can identify the following relationships from these execution sequences. And the first row here, the directly follows relationships, are essentially those that we have already represented in the directly follows graph. Many of them are actually also causal. But there's the exception. There's B followed by C and also C followed by B. That makes parallel relationships between these two activities. Any other pairs of activities are in an exclusiveness or in a so-called unrelated relationship. Now we can write down all these more complex relationships in terms of a footprint matrix. It's exactly the same information that we have seen on the previous slide. The reason for putting it into such a matrix is to help progressing with the alpha algorithm. The alpha algorithm now tries to identify different patterns of relationships. Each of these patterns is meant to be translated into a part of a BPMN model. The general idea is that when we observe that A causally leads to B, that we represent this in a BPMN model with two activities called A and B and an arc pointing from A to B. But what about gateways? In order to identify gateway structures, we have to look at least at 3 relationships in combination. For an XOR split pattern, we need to identify the relationship between A, B, and C in such a way that A causally leads to B, A also causally leads to C, and that B and C are unrelated. Correspondingly, if there is an XOR join, it would be a pattern that B causally leads to D, C causally leads to D, and B and C being unrelated. It might also be the case that a triple of relationships is of the following kind: that A causally leads to B, A causally leads to C, and B and C are known to be parallel. Correspondingly, if B leads to D and C leads to D, and B and C are parallel to each other, this is a pattern that would correspond to an AND join. The alpha algorithm now progresses over the footprint matrix and identifies various of these complex patterns. And with these patterns, it compiles them into a BPMN process model. Unfortunately, there are also some limitations. The alpha algorithm requires that all possible traces are actually also in the log. It also suffers from some technical challenges, that certain repeating behavior cannot be represented directly in the correct way. This is the case for self loops. That means when we observe that an activity is repeating in an event sequence, or for short loops. That means when an activity A is followed by B, and B is also followed by A. Now let's look at the heuristic miner. The difference between the alpha algorithm and the heuristic miner is that the heuristic miner takes frequencies into account. This means we get a transition matrix now, and the transition matrix captures the frequencies, how often we move from one event to another type of event. If you look at the matrix below, you can read that from A to B, we observe 11 different instances where this has happened. And indeed, we have 10 times the sequence A, B, C, E, and we have once the sequence A, B, E. This makes 11. Correspondingly, the matrix shows the number 11 in the cell in the first row A and the corresponding column B. Based on this transition matrix, we can now calculate a so-called dependency relationship. This is a measure how strong the relationship between an activity A and B is in one specific direction. You see that the formula from A to B is as follows. It is the number of times that A is followed by B minus the number of times that B is followed by A, subdivided by the number of times that A is followed by B plus the number of times B followed by A plus 1, in order to avoid to subdivide by 0. If A and B are the same activities, and this is the diagonal of the matrix that we need to consider, we subdivide A followed by A followed by A plus 1. Now, what can happen? Imagine that we observe 10 times that A is followed by B, but never B followed by A. The value for the formula is then 10 minus 0 subdivided by 10 plus 0 plus 1. This makes 10 divided by 11. And this is a strong indication that the direction from A to B is stronger. That means if we take this as an indication for a probabilistic consideration, we would rather draw an arc from A to B than from B to A. Based on this formula, we can calculate for each of the pairs of activities which kind of dependency they are associated with in a range between -1 and +1. If you look at the matrix at the bottom, you see that this is actually a matrix that is mirrored along the diagonal. If you look at the value from A to B, you see that the value is 0.92. If you look at the value for B to A, it is minus the exact same value. This is a property of this matrix. Now what can we do with these values is that we may use them for filtering. When drawing a graph, we might not be interested in the negative values. For filtering in abstraction, we might define positive thresholds for relationships to be included in a visual representation. You see a corresponding model for this event log here. The values are written. If you have looked carefully, you may have recognized that we also had cells of values 0.8, for example. The filtering has been applied such that these connections are not shown here. In this way, the diagram that you see is an abstraction of the event log. Filtering in abstraction brings a lot of freedom for the process analyst exploring the event log. But how can we do this more systematically? There are 4 different criteria that are associated with automatic process discovery. In the best case, we desire a process model that is produced by some automated discovery technique to be of minimal size and of limited structural complexity. We also hope that the process model is precise. Precision means that it does not include any extra behavior that we did not observe in the log. We also want a process model to fit the event log. That means it should actually capture all behavior that we observe in the log. Still, we would want the process model to generalize. One way of generalizing could be that we observe certain recurring sequences in our event logs. These could be potentially mapped to loops in our process models. So what could be now the problem? If we have a process model that has more behavior than what we have observed in the log, we would call this model imprecise. If there's more behavior in the log than what the model can represent, we speak of a lack of fitness. And if there's behavior that is possible according to the real-world process, we call it a lack of generalization. Generalization is most difficult because it is the log that we can observe about the process. The log doesn't tell us what could still be possible, which is not stored in it. In particular, precision and fitness can be used to fine-tune algorithms for automated process discovery. The following example may give you an idea that different process mining algorithms produce different output. Here, we see a process model that is produced by the Inductive Miner. Its key principle is to identify as much as possible structured behavioral parts in the event log. In this way, the Inductive Miner has identified 3 different passages of the process. There's apparently a first passage represented with an XOR block of looping back along the activities A, B, C, D, and E. There's a second choice block where choice has to be taken between F, G, H, and I. Finally, there's activity J. Now, for the same event log that is underlying this process, let's look at a different algorithm. For the same data, the structured miner has been able to increase the structuredness. We see here that while the inductive miner only identified one XOR block on the left-hand side of the model, the structured miner found some substructures. Apparently there's a choice between A and B. If B is taken, we continue with C. If A is taken, we have the choice between D and C or E. Note that the structured miner has shown C twice in the process model in order to make the model more structured. In this way, different process mining algorithms consider different trade-offs in order to come up with a good and nice representation of the underlying process.